There are probably a dozen videos sitting in your recommended feed right now explaining what an electron is made of. You have likely already watched one. They tend to go the same way. A little ball becomes a fuzzy cloud, the cloud becomes a wave, somebody says wave-particle duality with a certain amount of relish, and it closes out on the universe being a beautiful and mysterious place. If that is enough for you, honestly, that is fine. Click away. Nothing bad happens. But there is a paper in Nature from April of 2012, written by a group working at the Swiss light source, that almost none of those videos mention. In it, the electron's spin, its electric charge, and its orbital shape were observed coming apart from one another and travelling through a crystal at different speeds. 3 properties that every one of those other videos will tell you are intrinsic and inseparable. Separating, moving independently. That result is not the strange part of tonight. It is roughly the 6th strange thing in a row, because once you start pulling on this, the electron loses its surface, then its interior, then its shape, then its rotation, then the fixed value of its charge. And then, in a paper published in 1976 that has been sitting quietly in the textbooks for 50 years, it loses the one property everybody assumes is safe. The ability to be counted. Get comfortable and stay to the end, because by the time we get there you will not be able to think of the stuff you are made of as stuff. Episodes go up ad-free over on our Patreon, Meridian Labs, which this channel is part of along with a handful of others, and members get them early, plus the full research and source archive behind each one. Subscribe or join if you have not. Let's take it from the top. In 1988, a physicist in Seattle published a paper in which he gave a name to a single subatomic particle. He called it Priscilla. His name was Hans Dehmelt. He worked at the University of Washington, and he had spent years building a device called a penning trap, which is a bottle made out of nothing but fields. A strong, uniform magnetic field to keep the particle from drifting sideways, an electrostatic quadrupole to keep it from drifting along the axis, and a vacuum so hard and so cold that nothing else could get in. Into that bottle he put one positron, the antimatter twin of the electron, and he held it there, alone, for 3 months. In the paper, he explained the name. A particle that has been isolated and studied for that long, he wrote, deserves to be recognized by being given a name, just as pets are given names. I want you to sit with the strangeness of that for a second, because the naming was not sentimentality. What Dehmelt had built was the closest any human being has ever come to being in a room with a single fundamental particle and simply watching it. Not inferring it from a track in a cloud chamber, not reconstructing it from a spray of debris after a collision. One particle, in a bottle, for a season, being asked questions. And the title of that paper is where this gets interesting. It is called, in part, A New Value for the Electron Radius. What Dehmelt did with Priscilla, and with the electrons he trapped the same way, was measure how strongly the particle responds to a magnetic field. That number can also be calculated from theory. The two agreed to an absurd number of decimal places, and from the size of the agreement Dehmelt worked backwards to a limit on how big the electron is allowed to be. Less than 10 to the minus 20 centimeters. In meters, that is 10 to the minus 22. He did not measure a size. Hold on to that, because everything that follows depends on it. That number is not the width of anything. Read properly, it sets a ceiling. It says how much room is left over for the electron to have a width in, and by 1988, the room had become so small that the only honest reading of the result was that there is nothing in there having a width at all. For scale, a proton has a charge radius of about 840 atometers, which puts it just under 10 to the minus 15 meters across, and it is small enough that no analogy really works. But people try. If a proton were blown up to the size of a golf ball, an atom would be about the size of a large city. Dehmelt's ceiling on the electron is 10 million times smaller than the proton. And it is not a flaw. Nobody has ever found a bottom. Now think about the picture in your head. Almost everyone has the same one, because almost everyone got it from the same place. A little ball, negatively charged, whizzing around a nucleus in a neat orbit, like a planet, drawn in blue on a wall chart in a classroom that smelled of gas taps and disinfectant. That picture was already known to be wrong within about 13 years of being drawn. Niels Bohr proposed it in 1913. By 1926, it had been replaced by something that has no orbits, no paths, and no little ball. And it is still on the wall. It is still on the covers of textbooks and the logos of energy companies and the flags of nuclear agencies. It is the single most successful piece of obsolete science communication in human history. Here is where it gets worse, and this is the actual subject of the next 2.5 hours. We have known the electron exists since 1897. We have measured its magnetic properties to a precision better than 13 parts in 100 trillion, which makes it the most precisely tested object in the entire history of science, in any field, without exception. We can predict its behavior to more decimal places than we can measure the distance from here to the moon. Every piece of technology you have ever touched runs on our ability to push these things around with total confidence. Your screen, your nervous system, chemistry itself, the entire field, is the study of what electrons do. And there is no accepted answer anywhere in physics to the question of what one is. That is not a gap in popular understanding. It is not a case of the real explanation being too technical for a general audience. It is a gap in the physics. Open a graduate textbook on quantum field theory and go looking for the definition of the electron, and you will not find a description of an object. You will find a field, which is a mathematical assignment of numbers to every point in space and time. And you will find a rule describing what happens when you put energy into that field in a particular quantized way. The word electron appears as a label for that event, not for a thing, for an event. I have read a lot of these books over the last while, and I want to be honest about something. The first several times I noticed this, I assumed I was missing a chapter. I assumed the definition was somewhere earlier, in a foundational section I had skipped, and that the field language was a convenience for calculation that sat on top of a physical picture I would eventually be shown. It is not. There is no chapter. The field language is the physical picture, and when you ask the obvious follow-up question, which is what the field is made of or what it is a field in, the literature goes quiet in a way that is genuinely difficult to describe until you have gone looking for it yourself. And there is a version of this problem that is worse than not knowing what an electron is made of. Considerably worse. It is the question of whether there is a fact of the matter about how many electrons are in the room with you right now. I am going to leave that sitting there, because you are not going to believe it yet, and I have not earned it. But that question is not a philosophical aside, and it is not a thought experiment. There is a published result behind it, with 3 names attached and a date, and we will get there. What I want to do between now and then is walk you through every serious attempt physics has made to say what an electron is. In order. From a lecture hall in Nigsburg in January of 1897 to results published in the last 2 years, there are about 9 of these attempts depending on how you count, and every single one of them fails. That is the point. Not that they are wrong, most of them are extraordinarily right about what the electron does. They fail at saying what it is. And each one fails differently, and each failure takes away a different piece of what you thought was sitting there. The first takes away the surface, the next takes away the interior, then the volume, then the spinning. Then, in a result from 1997 that got a paragraph in the news and then vanished, the fixed value of the charge. And then, in a series of experiments from 2009 onwards, physicists in laboratories in Cambridge and Switzerland and Paris took an indivisible fundamental particle and pulled its properties apart from each other and watched them travel across a crystal at different speeds. That last one is real, it is in nature and science, it has been reproduced. And I would guess fewer than one person in 10,000 outside condensed matter physics has ever heard of it. That should make you angry. It makes me angry, and I have had months to get over it. We are going to end somewhere I did not expect to end when I started reading for this, which is why the thing I said earlier about counting electrons is going to matter, because the last attempt to say what an electron is does not fail by running out of precision. It fails in a much stranger way. It turns out that the question of how many particles are present in a region of space does not have a single answer that all observers agree on, and this has been known and published and accepted since 1976. But we should start where everybody starts, in 1897, with a discovery that did not happen the way you were told and was not made by the man whose name is on it. On the 7th of January, 1897, a 35-year-old physicist named Emil Weichert stood up in front of the Physical Economic Society of Nigsburg and told them that the rays coming off the cathode in a vacuum tube were made of particles, that those particles carried negative charge, and that they were somewhere between 2,000 and 4,000 times lighter than a hydrogen atom. Hydrogen was the lightest thing anyone knew about. It was the floor. It was, as far as chemistry in 1897 was concerned, the smallest unit of stuff that could exist, and still be stuff. Weichert was telling a room in East Prussia that he had found something a couple of thousand times lighter than the floor. Joseph John Thomson gave his version of the same claim at the Royal Institution in London on the 30th of April 1897, nearly 4 months later. There is a third man. Walter Kaufmann, working in Berlin, published measurements in the Annalen der Physik in 1897 that were, by most modern assessments, more accurate than Thomson's. Kaufmann had the numbers. He had them early. And he refused to say what they meant, because Kaufmann was a follower of Ernst Mach, and the Machian position was that physics should describe relationships between observable quantities and should not go around inventing invisible objects to explain them. Kaufmann had measured a ratio. He would talk about the ratio. He would not talk about a particle, because he had not seen a particle, and in his view neither had anyone else. Thomson got the Nobel Prize in 1906. Weichert became a seismologist. I want to be careful here, because the easy version of this story is that Thomson stole something, and that is not what happened. What happened is more interesting and considerably more uncomfortable. Thomson won because of what he was willing to claim. Weichert had the earlier date and the right order of magnitude, but he framed it cautiously and did not push it. Kaufmann had the better data and a philosophical commitment that forbade him from interpreting it. Thomson had somewhat worse numbers than Kaufmann and a later date than Weichert. And he stood up in front of the Royal Institution and said that this thing was a universal constituent of all matter, that every atom of every element contained them, and that the chemical elements were built out of them. He was right. He was also, by the standards of his own evidence, wildly overreaching. The prize went to the man who overreached. That pattern is going to repeat in this story more than once, and it is worth naming it now while it is still just an observation and not yet an indictment. The history of the electron is less a history of measurement than a history of interpretation, and the credit consistently goes to whoever was willing to say the uncomfortable thing out loud. The paper Thomson eventually published, in the October 1897 issue of the Philosophical magazine is called simply Cathode Rays. It is worth reading because it is far more hedged than the legend. In it he proposes that matter in the cathode ray tube has been split into a state in which the subdivision has been carried much further than in the ordinary gaseous state, a state in which all matter, whatever element it came from, is of one and the same kind. He does not call them electrons, he calls them corpuscles, and he kept calling them corpuscles for at least another decade, long after everyone else had stopped, because the word electron already meant something else. It had been coined in 1891 by an Irish physicist named George Johnstone Stoney, who used it to name a unit of electric charge. Not a particle, a quantity. Stoney had been arguing since 1874 that electricity came in discrete, indivisible lumps, and he wanted a word for the size of the lump. The word existed for 6 years before the thing did, and it originally referred to an amount, not an object, and I would argue that the physics never entirely recovered from that. Now here is the part that matters more than any of the priority arguments. Thomson never saw an electron. Neither did Weichert. Neither did Kaufman. Neither has anyone since. What Thomson actually measured was a ratio. He took a beam of something coming off a cathode, bent it with a magnet, bent it with an electric field, and worked out the relationship between the charge that beam was carrying and the mass it was carrying. In his notation it was m/e. Mass divided by charge. He got a number roughly 1,000 times smaller than the equivalent number for a hydrogen ion, and later refinements of the work pushed that towards the modern figure, which puts the electron at about 1/1836th of the mass of a hydrogen atom. A ratio is not an object. Thomson found that whatever was coming off that cathode carried a great deal of charge for very little mass. That is the entire experimental content of the discovery of the electron. Everything else, the ball, the size, the substance, the thing itself, is an interpretation laid on top of a measured ratio, and it was laid there by people who assumed that a measured ratio has to belong to something. The apparatus deserves a mention, because Thomson was famously bad with it. He was clumsy. His students would try to keep him away from the glassware. The delicate discharge tubes on which the entire discovery rested were built and operated by his assistant, a man named Ebenezer Everett, whose name is not on the paper and who does not appear in the Nobel citation. And the reason those tubes mattered is the best piece of physics in the whole story. Heinrich Hertz, one of the finest experimentalists of the 19th century, had tried the electric deflection experiment years earlier and had failed. The rays did not bend. Hertz concluded that cathode rays carried no charge and that they were some kind of disturbance in the ether, and his student Philip Lenard defended that position for years. Hertz was not careless, and he was not stupid. His vacuum was not good enough. The residual gas left in his tubes was being ionized by the beam itself, and those ions drifted to the walls and set up a counterfield that cancelled the field he was applying. He was applying an electric field to the beam, and the gas in his own apparatus was quietly cancelling it out. Thomson's tubes were emptier. That is the discovery. The entire 19th century argument about whether cathode rays were waves or particles came down to how much air you could get out of a glass bulb, and the man who could get the most out was working in a basement in Cambridge with a technician nobody remembers. While we are correcting things, 3 quick ones, because these misconceptions are load-bearing and they will get in the way later. Thomson did not split the atom, he did not break an atom apart. He pulled a stream of charged somethings off a hot metal plate and showed they were universal. The atom stayed intact. He also did not discover atomic structure. That was Ernest Rutherford, working partly with Thomson's own model in his sights, and we will get to what happened there. And Thomson did not discover that atoms contain electrons in any picture resembling the one you were shown. His model, published in 1904, is the one usually called plum pudding, and the usual description of it is wrong too. It was not a random scatter of raisins in dough. Thomson had the corpuscles arranged in rotating rings inside a sphere of positive charge. And he did real calculations on the stable configurations, and he was trying to explain the periodic table with them. It was a serious model. It was wrong, but it was serious. It lasted 5 years. In 1909, in Manchester, Hans Geiger and a 20-year-old undergraduate named Ernest Marsden fired alpha particles at a sheet of gold foil at Rutherford's suggestion, mostly as something to keep Marsden busy. Under Thomson's model, the alpha should have sailed through with only tiny deflections, because a diffuse cloud of positive charge has nothing dense enough in it to turn them around. Rutherford's paper of 1911 records what they actually found. About 1 alpha particle in 8,000, falling on a thick plate of platinum, came straight back at them. Rutherford's own description of that moment has been quoted so often that it has gone smooth, but read it slowly. It was quite the most incredible event that ever happened to me in my life. It was as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. What that experiment established is that the positive charge in an atom is concentrated into a volume roughly 100,000 times smaller than the atom itself, which means that the nucleus occupies about 1 part in 1,000 million of the space it sits in. Atoms are almost entirely empty. That much you probably knew. But that result did something else, and this is where the trouble starts. It took the electron out of the pudding and left it with nowhere to be. Thomson's corpuscles had been embedded in something. They had a medium. After 1911, they were alone in a vacuum, orbiting a tiny, dense nucleus across a distance so vast relative to their own scale that nothing was touching anything. And the moment you put a charged particle in a curved orbit, classical physics tells you exactly what happens next. It radiates, it loses energy, it spirals in. Do the arithmetic and every atom in the universe should collapse in about 10 picoseconds. Therefore, the question of what an electron is stopped being an academic one. It became urgent, because the existence of matter now depended on the answer, and the first serious attempt to give one involved deciding how big the thing actually was. There is a number that appears in physics textbooks called the classical electron radius. It is 2.818 femtometers, or 2.818 times 10 to the minus 15 meters. And if you look it up, you will find it listed among the fundamental constants, with a value quoted to 10 significant figures, sitting there next to the speed of light and the Planck constant as though it belongs. It is a fiction. It is not the radius of the electron, it has never been the radius of the electron, no experiment has ever supported it. And by the 1980s it was known to be wrong by a factor of at least 10 million. It is still in the tables. I find this genuinely funny in a way that is difficult to explain to people who have not spent time with the literature, because that constant was never a mistake that got left in. It stands as a monument to a project that failed, and the project it commemorates was the last serious attempt anyone made to say what an electron is out of materials that make sense. Here is where the number comes from, because you have to understand the logic to understand why the logic dies. Charge repels charge. If the electron has any size at all, then the charge spread over its surface or through its volume is repelling itself. Pushing the pieces of that charge together into a sphere therefore costs energy, and the smaller the sphere, the more it costs. The energy required goes up as the radius comes down, and if you shrink the radius to 0, the energy goes to infinity. Hendrik Lorentz and Max Abraham, working around the turn of the century, made the boldest possible move with this. They proposed that the electron has no separate mass at all. that everything we call its mass is just this stored electrical energy. Einstein's relation between mass and energy had not been published yet when the idea started, and when it arrived it made the proposal even more attractive, because now you could take the electron's known mass, convert it to an energy, set that equal to the electrical self-energy, and solve for the radius. 2.818 femtometers. That is where the number comes from. Nobody measured it. That is the size the electron would have to be if the electron were nothing but its own electric field wrapped around itself. I want to be fair to how good an idea this was. It is the most elegant answer to what is an electron that anyone has ever proposed. There is no substance in it, no mysterious stuff, no unexplained interior. The electron is a knot in the electromagnetic field, and its mass is the energy it takes to tie the knot. Lorentz spent the rest of his working life on it. He is remembered now for the transformations that carry his name and underpin special relativity, and almost nobody remembers that he derived them in the course of trying to build a mechanical model of the electron, and that he considered that project his real work, and that it failed. It failed for a specific reason, and the reason is worth the time. If the electron is a ball of charge, the charge is trying to blow the ball apart. The repulsion is enormous at that scale. Nothing holds it together. Henri Poincare, in 1906, patched this by proposing an additional non-electromagnetic pressure, an inward stress of unknown origin, which exists purely to keep the electron from exploding. These are called Poincare stresses, and they are still in the literature, and they are a confession written in mathematics. The electron cannot be made of electromagnetism alone, because electromagnetism alone tears it apart, so we posit something else, and we cannot say what the something else is, and it has no independent evidence. And its only job is to prevent the theory from destroying its own subject. That should have been the end of it. It was not. It got worse. Because a charged object that accelerates radiates energy, and if it radiates energy it must feel a recoil, and if you write down the equation for that recoil for a point charge, you get something called the Abraham-Lorentz force. Paul Dirac produced the relativistic version of it in 1938 in a paper on the classical theory of the radiating electron. The equation contains the third derivative of position with respect to time. Not velocity, not acceleration, the rate of change of acceleration. And an equation of motion with a third derivative in it has solutions that ordinary mechanics does not have. And two of those solutions are catastrophic. The first is called the runaway solution. Take a free electron, apply no force to it whatsoever, and the equation permits it to accelerate spontaneously, exponentially forever, its acceleration doubling on a timescale of about 10 to the minus 24 seconds, drawing unlimited energy from nowhere. You have to throw that solution away by hand. There is nothing in the physics that forbids it. The second one is worse, and it is the reason I am spending time on a theory nobody uses. If you throw out the runaway solutions by imposing the requirement that the acceleration must go to zero in the far future, the remaining solutions have a property called pre-acceleration. The electron begins to move before the force arrives, not metaphorically. The equation, honestly solved, describes a particle that starts accelerating a short time before the field that pushes it reaches it. The interval is tiny, roughly 10 to the minus 24 seconds, comparable to the time light takes to cross the classical electron radius. But it is not zero, and its sign is wrong. And what it means is that the classical theory of the point electron violates causality. This is not fringe, and it is not a crank result. You will find it in Jackson's Classical Electrodynamics, which is the standard graduate text, the one that every physics doctoral student in the English-speaking world has suffered through. It is a known, published, unresolved pathology at the foundation of the most successful classical theory ever written, and the honest summary of the situation is that if you take seriously the idea that the electron is a small charged object, then either the object can accelerate itself to infinity for free, or it can respond to things that have not happened yet. Physics did not solve this. I want to be blunt about that, because the textbook treatment tends to present the point particle as a simplification that works well enough, and that framing is a kindness that obscures what actually took place. Physics did not solve the classical electron. It stopped asking. The quantum theory arrived. It was spectacularly successful at predicting what electrons do, and the question of what the electron is was quietly reclassified as the sort of thing that serious people do not spend their careers on. The move that made it possible to stop asking was to take the radius to 0. Not a very small radius. 0. A mathematical point, with no extent in any direction, carrying a definite mass and a definite charge, and as we will see, a definite angular momentum, occupying no volume whatsoever. And you cannot do that. That is the thing. Setting the radius to 0 does not remove the self-energy problem, it makes the self-energy exactly infinite. It does not soften the divergence, it maximizes it. Every quantity in the theory that involved the electron interacting with its own field became infinite the moment the radius became 0, and those infinities did not go away in the quantum version. They got worse, and they multiplied. The way physics eventually dealt with those infinities is one of the strangest episodes in the history of science. It is the reason we can predict the electron's magnetic moment to 13 parts in 100 trillion, and the man who wrote the original equation spent the last 30 years of his life saying in public that the method was not sensible mathematics, and that the entire theory would have to be torn down and rebuilt. We will get to Dirac. First, though, there is a more immediate question, because you may have noticed a gap in what I have said so far. If the classical radius is a fiction, and the theoretical radius is 0, what have the experiments actually found? How hard have people looked? They have looked extremely hard, and what they found is not that the electron is small. What they found is stranger than that, and it took until roughly 1979 before anyone worked out why it could not be otherwise. The way you find out how big something is when it is too small to see is that you throw things at it and watch how they bounce. That is what Rutherford did to the atom. It is what everyone has done since. If a target has structure, then when you hit it hard enough, the scattering pattern changes, because you start resolving the pieces rather than the whole. This is exactly how the proton was found to contain quarks at the Stanford Linear Accelerator in 1968. You fire electrons at protons at high enough energy, and suddenly the electrons start bouncing off hard little somethings inside, and the pattern of the bouncing tells you there are 3 of them. The same technique, applied to electrons, has been running for over 50 years at Petra in Hamburg, at SLAC in California, at the Large Electron Positron Collider at CERN, which was a ring 27 kilometers around buried under the French-Swiss border, and which ran from 1989 to 2000. Nothing has ever bounced off anything. The way you quote that result is as an energy scale, because in this kind of physics, energy and distance are 2 ways of saying the same thing. Higher energy means shorter wavelength, means finer resolution. The limits from the collider experiments put any possible electron substructure at an energy scale of several teri-electron volts, which corresponds to a size below about 10 to the minus 18, or 10 to the minus 19 meters. And then there is Dehmelt's number, the one we started with, which comes from an entirely different direction, not from smashing electrons together, but from watching one sit still and measuring how it responds to a magnetic field. 10 to the minus 22 meters. Put those numbers next to something familiar. An atom is about 10 to the minus 10 meters across. A proton is 10 to the minus 15, Dehmelt's ceiling on the electron is 10 to the minus 22. The gap between an atom and a proton is a factor of 100,000. The gap between a proton and the ceiling on the electron is 10 million. Here is the analogy that finally made this land for me. If you scaled a hydrogen atom up until it was the size of the Earth, the proton at its center would be about 200 meters across, roughly a large office block, and the electron, on that same scale, using the tightest bound anybody has ever placed on it, would be a speck about 1/100th of a millimeter across. A single human cell, everything else about that atom, all of its chemistry, all of its bulk, all of the reason your hand does not pass through a table, is generated by the office block and the thing smaller than a virus and the enormous empty distance between them. Now, the standard response to all of this is the reasonable one. We have not found structure yet. Perhaps we need more energy. Perhaps in 50 years a bigger machine will crack it open and find the pieces the way the proton was cracked open in 1968. That is the reasonable assumption, and there is a specific argument worked out in the 1970s and refined since that says it cannot happen. Not that it has not happened. That it cannot. In the 1970s, a lot of very good physicists went looking for the layer below. The models had names. Jogesh Patti and Abdus Salam coined the term prion in 1974 for the hypothetical constituents. Haim Harari and Michael Shoup independently produced a model in 1979 built from just two constituents, which Harari called rishons, from the Hebrew for primary, and which could generate every known quark and lepton in the first generation from combinations of two objects. It was beautiful. It was economical in a way that the standard model has never been. It reduced the entire particle zoo to two ingredients. It is dead, and what killed it is a piece of reasoning so simple that you can follow every step of it, and once you have followed it, the electron will never look the same again. Take Heisenberg's uncertainty principle, which is not a statement about measurement disturbance, whatever you are told. It is a statement about what it means for something to be confined. If you localize a quantum object to within a distance, its momentum acquires a spread inversely proportional to that distance. Squeeze something into a small box and it starts moving fast. Not because you disturbed it, because being in a small box and having a definite slow speed are mathematically incompatible descriptions. We have just established that the electron shows no structure down to about 10 to the minus 18 meters. Therefore, if there are constituents inside it, they are confined within a region of at most that size. Run the uncertainty principle on that number, and you find that each constituent must carry a momentum corresponding to an energy of roughly 200 gigaelectronvolts. The electron's entire rest energy is 0.511 megaelectronvolts. 200 gigaelectronvolts is 200,000 megaelectronvolts. The constituents would each need to carry about 400,000 times more energy than the finished electron weighs. Sit with that. For an electron to be composite, the kinetic energy of the pieces racing around inside it would have to be cancelled, almost perfectly, by a negative binding energy holding them together, and the cancellation would have to be accurate to about 1 part in 400,000, leaving behind exactly the sliver we call the mass of the electron, and it would have to work for the muon, which is 200 times heavier, and for the tau, and for the up quark and the down quark and the neutrinos, each to a different and equally precise degree, each by a separate miracle, with no mechanism proposed for any of them. Compare that to the proton, which really is composite. The proton weighs about 938 megaelectronvolts. Its 3 valence quarks, added up, weigh around 9. The proton is heavier than its ingredients, by a factor of roughly 100 because the binding energy adds. That is what compositeness normally looks like. The whole is heavier than the parts, and usually a great deal heavier. The electron would have to be almost 500,000 times lighter than its parts. This is why the electron is treated as fundamental, and I think the reason is almost never explained properly to the public. The usual line is that no substructure has been observed, which sounds like an absence of evidence and invites the assumption that the evidence is coming. The situation is different. What the argument establishes is that the electron's own lightness forbids it from having an inside. The lighter a composite object is relative to the confinement scale, the more fine-tuned its internal cancellation has to be. And the electron is so light and so point-like that the required tuning stopped being a research problem and became an embarrassment. The electron is not small. Small is a category that applies to objects. The electron has no measured extent and, if the argument I just walked you through holds, cannot acquire one without breaking something else. I said earlier that each attempt to define the electron takes away a different piece. That is the second piece gone. There is no interior. Not an interior we have failed to resolve. An interior that the mass budget of the particle will not permit to exist. Which leaves you with a genuinely uncomfortable object. Something with a definite mass, a definite charge, a definite magnetic moment, and no volume for any of those properties to be distributed through. Every property concentrated at a mathematical point with zero size. And there is something I keep coming back to, and I want to flag it now because it is going to become the whole argument by the end. Every single number I have quoted you about the electron is a number describing what it does to something else. The mass is defined by how it resists being pushed. The charge is defined by how hard it pulls on other charges. The magnetic moment is defined by how it turns in a magnetic field. Its size is inferred from how things bounce off it, and nothing bounces off it. There is not one measured property of the electron that is a property of the electron on its own. There is no intrinsic measurement. There cannot be, because there is no interior to look into and no surface to look at. Everything we know about the most precisely measured object in the history of science is a description of its relationships. You could reasonably say that this is true of everything, that all measurement is relational, and philosophically you would have a point. But with a rock or a proton or a hydrogen atom there is something there in addition to the relationships. There is stuff you could in principle look at. With the electron there is nothing left over. Take away the relationships and there is no residue at all. Hold that. Because when we get to the end of this, the question is not going to be what the electron is made of. The question is going to be whether there is anything there at all when nobody is interacting with it, and there is an experiment that bears on this, and it does not go the way you would want. Before that, though, we have to deal with the geometry, because a point particle with mass creates a problem that has nothing to do with quantum mechanics and everything to do with gravity. If you put a finite mass into a zero volume, you have written down infinite density. And there is a well-developed branch of physics that deals with what happens when you do that. Before I go into the gravity, I want to sharpen the thing I left hanging at the start, because we have now reached the point where it stops sounding like a rhetorical device. I asked earlier whether there is a fact of the matter about how many electrons are in the room with you. Here is why that is a real question rather than a clever one. If the electron has no interior and no extent, and every property we can measure is a description of how it interacts with a detector, then the word electron is doing a job it was never designed for. It was coined for an amount of charge, then repurposed for an object, and we have now established that the object has no inside, no outside, and nothing about it that is not a relationship. What is left is a count. However many of them there are, at least we can count them. That is the last thing about the electron that feels solid, and it is the thing that goes last. And when it goes, it takes more with it than you would expect. Now, gravity. If you take the electron's mass and ask general relativity what radius that mass would have to be squeezed inside for it to form a black hole, you get the Schwarzschild radius, and for an electron it comes out at about 1.35 times 10 to the minus 57 meters. That number is meaningless in isolation, so here is the comparison that matters. The scale at which quantum mechanics says you can no longer sensibly talk about where an electron is located is called the Compton wavelength, and for the electron it is 2.43 times 10 to the minus 12 meters. That is not small. It is about 1/20th of the radius of a hydrogen atom, and a couple of 100 times larger than an atomic nucleus. The ratio between those two numbers is around 10 to the 45th. 10 to the 45th. If you spent 1 second on each unit, counting up to 10 to the 45th would take you around 10 to the 37th years, and the universe is currently about 1.4 times 10 to the 10th years old. You would need to run that count for longer than the present age of the universe, 10 to the 27th times over. That gap is why the electron is not a black hole. Gravity never gets a chance. The quantum fuzziness of the electron's position is 45 orders of magnitude wider than the scale at which its own mass would close a horizon around it. You cannot compress it, because there is no it to compress, and the position is not a fact that can be sharpened past a limit. Fine. Except general relativity has more than one way to describe a compact object. And if you feed it the electron's actual properties, all three of them, it returns something that nobody has ever known what to do with. The most general known solution for a stationary object in general relativity is the Kerr-Newman metric. It describes space-time around a mass that also carries electric charge and angular momentum. It was completed in 1965, building on Roy Kerr's rotating solution from 2 years earlier. And it comes with a condition. The solution describes a black hole only if the mass squared is greater than or equal to the square of the angular momentum per unit mass plus the square of the charge. If that inequality holds, you get an event horizon and everything behaves. If it fails, the horizon does not form, and what is left behind is a singularity with nothing covering it. A naked singularity. A region of infinite curvature that is not hidden, that light can leave, that in principle you could look at. Physicists hate naked singularities. Roger Penrose proposed the cosmic censorship conjecture in 1969 specifically to argue that nature does not produce them, that every singularity formed by realistic gravitational collapse comes politely wrapped in a horizon. Cosmic censorship is unproven. It is a hope with a formal name. Now put the electron's numbers into the Kerr-Newman condition. The electron's charge, expressed in the units where the comparison makes sense, exceeds its mass by about 21 orders of magnitude. Its angular momentum per unit mass exceeds its mass by about 22 orders of magnitude. The inequality is not marginally violated. It fails by something on the order of 44 orders of magnitude. An object with the electron's charge, the electron's mass, and the electron's spin does not have an event horizon. General relativity, asked to describe an electron, hands back a spacetime with a naked ring singularity sitting in the middle of it. And then it gets strange in a way that I have not been able to put down since I first read it. In 1968, Brandon Carter, a young Australian physicist working in Cambridge, was studying the global structure of Kerr-Newman spacetimes. He calculated the gyromagnetic ratio of the solution. That is the number describing how strongly a rotating charged object responds to a magnetic field, the same number Dehmelt was measuring 20 years later with Priscilla in the trap. For any ordinary rotating charged object, a classical physics gives a gyromagnetic ratio of 1, a spinning charged sphere, a current loop, a planet with a charge on it, all of them give 1. The electron gives 2, and that factor of 2 was was one of the great puzzles of the 1920s, and it was only explained when Dirac wrote down his relativistic equation in 1928, and the two fell out of the mathematics. Carter found that the Kerr-Newman solution also gives exactly two, a charged rotating hole in spacetime described entirely by general relativity, with no quantum mechanics anywhere in the derivation, has the same anomalous gyromagnetic ratio as the electron. I want to be careful because this is exactly the sort of result that gets picked up and turned into something it is not. Nobody serious claims the electron is a naked singularity. The Kerr-Newman solution for the electron's parameters has pathologies. There are closed time-like curves in it, which means paths through space-time that return to their own past. There is no accepted theory connecting the two descriptions, and the coincidence of the gyromagnetic ratio has a reasonably well-understood mathematical origin that does not require the objects to be the same thing. But I also want to be honest about how it feels to sit with it. We have a particle with no size. We ask the best theory of gravity we have what space-time looks like around such an object. It tells us there is no horizon, and there is a naked singularity, which is the one thing the entire field has spent 50 years hoping does not exist. And then, it independently reproduces the single most distinctive number the electron has. A number that took a quantum revolution to explain, and it does it for free. The literature on this is small, and it is polite, and it mostly appears in general relativity journals rather than particle physics ones, and I would describe the mainstream attitude towards it as a kind of studied lack of curiosity, not suppression. Nobody is stopping anybody. It is that there is no career in it, no experiment that could test it, no grant line it fits under, and so a genuinely peculiar structural coincidence at the intersection of the two most successful theories in physics sits in the literature being cited about as often as a paper on the taxonomy of beetles. That is the third piece gone. Not just no interior and no surface. Now the geometry itself refuses to close around it. There is no shape here. There is a location where properties are, and even that turns out to be generous. Because the location is not a point in any sense you would recognize either. Therefore, we should look at the property that seems most obviously physical, the one that everyone thinks they understand, the one that gets drawn with a little arrow on it in every diagram. The electron spins. Everyone knows that. It does not spin. And the story of how physics found that out involves a graduate student trying to withdraw his own paper in a panic, a supervisor who had already posted it, and a man who worked out the right answer 8 months earlier and was talked out of publishing by the most feared physicist in Europe, in January of 1925. A 20-year-old German-American physicist named Ralph Kronig arrived in Tübingen. He was shown a letter from Wolfgang Pauli containing an idea about a fourth quantum number, a two-valued property of the electron that nobody could account for. Kronig read it, went away, and came back the next day with an interpretation. The electron is spinning. It has intrinsic angular momentum, half a unit of it, and that is the two-valued property. He worked out the consequences, he got the right structure, and he got a factor of 2 wrong in the fine detail, which nobody could have avoided at that point, because the correction required relativity and had not been discovered yet. Then he showed it to Pauli. Pauli was 24 and already terrifying. His response is recorded. The idea, he said, was indeed very clever, but of course had nothing to do with reality. Kronig did not publish. He put the calculation away. He went on to a perfectly good career and made real contributions and died at 89, and he spent the rest of his life having been the first person to understand electron spin and having nothing to show for it, because a man his own age told him it was silly. 9 months later, in Leiden, 2 graduate students working under Paul Ehrenfest had the same idea. George Uhlenbeck and Samuel Goodsmit wrote it up as a short note. Ehrenfest read it, thought it was worth publishing, and sent it to the journal Naturwissenschaften. It is dated the 17th of October, 1925. Then Uhlenbeck went to see Hendrik Lorentz, who was by then in his 70s and the most respected physicist in the Netherlands, and Lorentz did the calculation that Kronig had not done. If the electron is a spinning ball of charge, and if it has the angular momentum the model requires, then how fast is its surface moving? You take the angular momentum, you divide by the mass and the radius, and you get a speed. Lorentz took the classical electron radius, the 2.818 femtometer number from the failed Lorentz-Abraham model, ran the arithmetic, and found that the surface of the electron would have to be moving at many times the speed of light. Depending on which radius you assume and how you set the calculation up, the figures people quote run from about 10 times the speed of light to around 137 times it. The exact factor does not matter. It is not close, and it is not a matter of a small correction. The model misses by 2 orders of magnitude in a quantity that relativity says has a hard ceiling. Uhlenbeck went to Ehrenfest in a panic and asked him to withdraw the paper before it appeared. Ehrenfest told him it had already been sent. And then he said the thing that everyone in physics knows and almost nobody can source properly, which is that the two of them were young enough to be able to afford a stupidity. The paper went out. It was right. The factor of 2 that both Kronig and the Leiden pair had wrong was fixed in 1926 by Llewellyn Thomas, using a relativistic effect on rotating reference frames that is now called Thomas precession, and after that the theory of spin was correct and complete and predicted the spectra beautifully, and the ball was still moving faster than light. Nobody has ever fixed that. Let me be precise about what I mean, because this is one of those places where the standard account is technically true and practically misleading. The way the problem was resolved was by declaring that the electron does not rotate. That spin is an intrinsic form of angular momentum with no classical analogue, a property the electron simply has in the same way it has charge, requiring no motion of anything through space and no interior to do the moving. That is correct. It is also, if you look at it straight, a restatement of the problem in language that makes it sound like an answer. The electron possesses angular momentum. Angular momentum is, in every other context in physics, a measure of rotation. This one involves no rotation whatsoever. Angular momentum, with nothing going round. I have read a lot of attempts to explain this, and the good ones all eventually admit the same thing. There is no picture. You are being asked to hold a quantity that is defined by circular motion, and to subtract the motion and the circle and keep the quantity. And before anyone thinks this is a philosopher's complaint about language, spin has consequences that are not remotely abstract, and one of them is the strangest experimental result in this entire story. If you rotate an ordinary object through 360 degrees, it comes back to how it started. That is what a full turn means. It is arguably what the number 360 is for. An electron does not. The quantum state of an electron, rotated through a full 360 degrees, comes back with its sign flipped, not the same state, the negative of it. To return an electron to the state it was actually in, you have to turn it through 720 degrees. 2 full revolutions. This is a consequence of the electron being described by a mathematical object called a spinor rather than by a vector, and for 50 years it was the sort of thing that lived in the formalism and got waved at in lectures, because the sign of a quantum state is not directly observable. You can only see it if you can interfere the rotated electron with an unrotated copy of itself and watch the interference pattern invert. In 1975, 2 groups did exactly that. Helmut Rauch and colleagues in Vienna, working at a research reactor, and Samuel Werner and colleagues in Missouri independently built neutron interferometers. Neutrons, like electrons, are spin 1/2 particles, and they are much easier to send through a crystal interferometer. You split a neutron beam in two, you send one arm through a magnetic field that rotates its spin by a controlled amount, you recombine them, and you watch the interference. The prediction is that the interference should invert at 360 degrees and only return to normal at 720. Rauch's paper, published in Physics Letters A, is titled The Verification of Coherent Spinor Rotation of Fermions. Later precision runs measured the periodicity directly and got 715.87 degrees, plus or minus 3.8. 720 degrees with an experimental error, that is a measured fact about the universe. Turn a fermion all the way around and it is not the same. Turn it all the way around again and it is. There is no version of a small spinning ball that does this, no version of a wave, no version of any classical object at all. The space of rotations that the electron lives in is not the space of rotations that you live in, and the experiment was done 50 years ago, and I would guess a good proportion of working physicists could not tell you it had been done at all. Here is a misconception worth killing while we are here, because it is everywhere. The Stern-Gerlach experiment did not discover spin. Otto Stern and Walther Gerlach fired a beam of silver atoms through a non-uniform magnetic field in 1922, 3 years before spin was proposed, and found that the beam split into two distinct spots rather than smearing into a continuous band. It is taught as the demonstration of electron spin. At the time, everyone including Stern and Gerlach interpreted it as confirmation of the Bohr-Sommerfeld quantization of orbital angular momentum, which is a completely different thing, and which was wrong. The correct interpretation did not arrive until 1927. The experiment that everyone cites as proving spin was, for 5 years, understood to be proving something else, and its authors did not realize what they had found. There is also a detail about that experiment that I find hard to stop thinking about. The silver deposit on the detector plate was too thin to see. It only became visible because Stern smoked cheap cigars, and the sulfur in the smoke reacted with the silver film and turned it black. The result that opened quantum mechanics was developed by tobacco. I want to come back to Ehrenfest, because I promised you the human thread, and because his story is the one that has stayed with me longest out of everything I read for this. Paul Ehrenfest was born in Vienna in 1880. He held the chair at Leiden that Lorentz had held. He was, by universal agreement, one of the finest teachers physics has ever produced, and one of its sharpest critics, the man everyone sent their papers to, because he could find the weak point faster than anyone. Einstein called him the best teacher in the profession he had ever known, and considered him one of his closest friends. He was also, throughout his adult life, severely depressed, and the depression got worse as the 1920s went on. Part of it was political, and he could see what was coming in Germany from a country next door. Part of it was that he had become convinced he could no longer follow the physics. The quantum theory he had helped to midwife had gone abstract and mathematical in a way he found alienating, and he wrote to friends that he could not keep up, that the field had left him behind, that he no longer understood what he was doing. He wrote a letter in 1932 to Bohr, Einstein and others, saying he had completely lost the ability to assimilate any new theoretical idea, and that he felt his continued existence was pointless. His friends did not know what to do with it. On the 25th of September, 1933, in Amsterdam, Paul Ehrenfest killed his youngest son, who had Down syndrome and was living in an institution, and then killed himself. He was 53. The man who told 2 graduate students they were young enough to afford a stupidity did not think he could afford anything anymore, and the idea he sent out into the world over their objections is still there, still correct, still unexplained. The electron has angular momentum. Nothing is turning. Turn it around once, and it comes back inverted. Nobody knows why. Which brings us to the equation that made the spin fall out of the mathematics for free, and to the man who wrote it, and to what happened when he watched his own theory get saved by a procedure he considered a fraud. Paul Dirac was born in Bristol in 1902 to a Swiss father who insisted the children speak to him only in French at the dinner table, and who punished mistakes, and who ate with Paul alone in the dining room while the mother and the other two children ate in the kitchen. Dirac said later that he grew up believing conversation was something that could only be done badly and was therefore best avoided. He became the most silent man in physics. His colleagues at Cambridge defined a unit called the Dirac, being 1 word per hour. In March of 1925, his older brother Felix, who had wanted to be a doctor and had been pushed into engineering by the same father, took his own life. Dirac wrote about it only once, decades later, and what he said was that he had not previously realized parents were supposed to care about their children. 3 years after that, at the age of 25, he wrote down an equation that is on his memorial stone in Westminster Abbey. What Dirac was trying to do was combine quantum mechanics with special relativity, which had resisted every previous attempt. Schrödinger's equation is not relativistic. It treats space and time differently, which relativity forbids. Dirac went looking for a version that treated them the same way and that still gave sensible probabilities, and what he found was that it could be done, but only if the wave function had 4 components instead of 1. 2 of those components turned out to describe spin. It was not put in. Dirac was not trying to explain spin. He was trying to satisfy relativity, and out of the requirement that the equation be first order in both space and time, the 2-valued intrinsic angular momentum of the electron simply appeared, along with a gyromagnetic ratio of exactly 2, which had been an unexplained empirical fudge for 3 years. That is what a great equation does. You ask it one question, and it answers a different one you had not thought to ask. The other 2 components were a problem. They described states with negative energy, an infinite ladder of them going down forever, and there was no obvious way to throw them away because the mathematics needed them. Dirac's eventual answer in 1931 was that these states are all already occupied, everywhere, filling the vacuum, and that a hole in that occupied sea would behave like a particle with the same mass as the electron and the opposite charge. In 1932, Carl Anderson at Caltech photographed a track in a cloud chamber that curved the wrong way. He published it in 1933. It was the positron, and it was the first piece of antimatter anyone had ever seen, and it had been predicted on paper by a silent Englishman working from nothing but the demand that an equation be consistent. It was, at that point, reasonable to think physics was about to close the case on the electron. It had an equation. The equation predicted its spin, its magnetic moment, its antiparticle, and the fine structure of the hydrogen spectrum, all correctly. Then people tried to calculate anything to higher precision, and every answer came out infinite. The reason traces straight back to the point particle. In quantum field theory, the electron does not sit alone. It continuously emits and reabsorbs virtual photons, and those photons can briefly become electron-positron pairs, which emit further photons. Every one of those processes contributes to the electron's measured properties, and when you add up the contributions, you are summing over every possible energy the virtual particles could have, all the way up to infinity, and the sum diverges. Not approximately. Not in a way that a better approximation would fix. The theoretical prediction for the electron's mass, and its charge, and every quantity you tried to compute past the leading order came out as infinity. For about 18 years, that was the state of the art. The best theory of matter available to physics gave the answer infinity to almost every question, What broke it open was a measurement. In 1947, Willis Lamb and Robert Rutherford at Columbia used microwave techniques developed for wartime radar to look very carefully at two energy levels in hydrogen that the Dirac equation said should be exactly equal. They were not equal. They were separated by a frequency of about 1000 megahertz. The modern figure is 1057.8. That gap should not exist. Dirac's equation, the Great Equation, said 0, and the experiment said 1000 megahertz. From the 2nd to the 4th of June, 1947, about 25 physicists met at a small inn on Shelter Island, off the eastern end of Long Island. It was the first proper American physics conference since the war, and everyone there had spent the previous 5 years building weapons. Lamb presented the shift. Isidore Rabi presented a related measurement from his group, showing that the electron's magnetic moment was not exactly 2 after all, but slightly more. Hans Bether left the conference and got on a train to Schenectady, and on the journey, roughly 75 miles, he did a calculation on the back of whatever he had with him. His idea was borrowed from Hendrik Kramer's. The infinite self-energy of a free electron is unobservable, because you never measure a free electron without its own field. The mass you measure in the laboratory already contains it. Therefore, if you want to know how much the energy shifts when the electron is bound in an atom, you should subtract the free electron's infinite self-energy from the bound electron's infinite self-energy, and hope that what is left over is finite. It was. Bethe got a number close to 1000 megahertz. He published it within weeks. That subtraction is called renormalization. Between 1947 and 1949, Shinichiro Tominaga in Tokyo, Julian Schwinger at Harvard, Richard Feynman at Cornell, and Freeman Dyson at Cornell turned it into a complete and consistent procedure, and quantum electrodynamics became the most accurate theory in the history of human thought. I want to make sure the shape of what happened there is clear, because the popular telling smooths it into a triumph, and it was not only a triumph. The bare mass of the electron in quantum electrodynamics is infinite and negative. The self-energy contribution is infinite and positive. You add an infinite negative number to an infinite positive number, and you declare that the result is 0.511 megaelectron volts, because that is what the scales say. The infinities are not cancelled by a mechanism. They are cancelled by fiat, in a way that is mathematically consistent and internally rigorous, and that gives correct answers to more decimal places than any other prediction in science, and that nobody has ever been able to derive from anything more fundamental. Dirac never accepted it. Not in a grumbling elder statesman way. He said it, repeatedly, in print, in lectures, for the last 3 decades of his life. In a lecture given in 1975, he put it like this. He said he was very dissatisfied with the situation, because this so-called good theory does involve neglecting infinities which appear in its equations, neglecting them in an arbitrary way. This is just not sensible mathematics. Sensible mathematics involves neglecting a quantity when it turns out to be small, not neglecting it just because it is infinitely great and you do not want it. Elsewhere he described it as a stopgap procedure, and said that the change required to fix it would have to be as fundamental as the change from Bohr's orbits to quantum mechanics, and that in a correct theory the infinities would never arise in the first place. Feynman, who won a Nobel Prize for it, agreed with him. In his 1985 book on quantum electrodynamics, written for general readers, he called the procedure a shell game, said that no matter how clever the word renormalization is, it is still what he would call a dippy process. That having to resort to such hocus pocus has prevented us from proving that quantum electrodynamics is mathematically self-consistent, and that he suspected renormalization is not mathematically legitimate. 2 of the 4 men most responsible for the most successful theory in physics said in public that they did not believe the central move in it was valid mathematics. That is worth stopping on, because I do not think it is widely known, and nobody has hidden it. You can read it in a mass-market paperback. It is in Dirac's collected lectures. It is taught sort of in graduate courses, in the sense that the students are told that the founders had reservations, and then are handed the calculational rules and told to get on with it. And the rules work. This is the part that makes the whole thing feel less like a scandal and more like a haunting. Remember Dehmelt and Priscilla. The quantity being measured there is the electron's magnetic moment, and the amount by which it exceeds Dirac's clean prediction of 2 is called the anomaly. Dirac says 2. Reality says a bit more. The excess comes entirely from those virtual processes, the ones that give infinity if you calculate them naively. Calculating the anomaly means summing a series of corrections. The first correction was done by Schwinger in 1948, and he had it carved on his headstone. The second requires 7 diagrams. The third, 72. The fourth, 891. The fifth order term, computed by Tadashi Aoyama, Toichiro Kinoshita and Makiko Nio, and revised over many years, required the evaluation of 12,672 separate Feynman diagrams. That result was independently re-verified by a different group in 2024. In February of 2023, a group at Northwestern published in Physical Review Letters the most precise measurement of the electron magnetic moment ever made. The value has 14 digits after the decimal point. Its fractional precision is 13 parts in 100 trillion. Theory and experiment agree across all of them. There is a companion measurement that I think is even odder, and it involves asking a question that should not be answerable. You can ask whether the electron's charge is distributed symmetrically, whether there is a slight excess of negative charge towards one end of it, along the axis of its spin, which would make it very faintly pear-shaped rather than perfectly round. That quantity is called the electric dipole moment of the electron, and a non-zero value would violate time reversal symmetry and would be direct evidence of physics beyond the standard model, which is why people have been chasing it for 60 years. In 2023, a group at Gila in Colorado, using trapped hafnium fluoride molecular ions in rotating electric fields, published the tightest limit anyone has achieved. The electron's dipole moment is smaller than 4.1 times 10 to the minus 30 in the standard units, which are electron charges times centimeters. The usual way of expressing what that means is that the electron is the roundest object ever measured. The comparison people reach for is that if you scaled an electron up to the size of the solar system, its departure from a perfect sphere would be less than the width of a human hair. That comparison is an illustration rather than an arithmetic result, and I would not defend the exact numbers, but the order of the thing is right. Now hold that next to everything I have already told you. There is no measured size. There is no surface. There is no permitted interior, and we have determined the shape of it to 30 decimal places. What is actually being measured, of course, is the shape of the field configuration, the way the disturbance is distributed in the space around where the electron is said to be. Which is another way of saying that even the roundness belongs to the region rather than to the particle. And the standard model's own prediction for this quantity is around 10 to the minus 44, which is 14 orders of magnitude below where the experiments currently sit. There is a vast unexplored gap between what has been ruled out and what the theory expects, and every improvement in the limit over the last 2 decades has found nothing, which has quietly killed several proposed extensions of particle physics without anyone outside the field noticing that a search was even running. Here is what that means. Put plainly, physics can predict the behavior of the electron to a precision equivalent to measuring the distance from the Earth to the Moon and getting it right to within the width of a few human hairs. And to do it, you have to take an infinite quantity, subtract another infinite quantity from it, keep the finite remainder, and refuse to ask what happened. That is the fourth piece gone. We now have an object with no surface, no interior, no volume, no rotation, and a set of properties that can only be calculated by a procedure its own architects described as hocus pocus. But the charge, at least, is a fixed number. Every electron carries exactly the same charge, 1.60 2 times 10 to the minus 19 coulombs, defined as exact since 2019. That is bedrock. Except it is not, and the experiment that showed it is not was done at CERN in the 1990s and is one of the most underappreciated results in modern physics. Robert Millikan measured the charge of the electron between 1909 and 1913 by spraying a fine mist of oil into a chamber, letting the droplets pick up charge, and balancing them in mid-air against an electric field. Watch a droplet fall, measure its speed, work out its size and mass from how the air resists it, then switch on the field and see what voltage holds it still. The charge on the droplet comes straight out. Do it for thousands of droplets, and the charges all turn out to be multiples of a single smallest value. He got about 1.59, 2 times 10 to the minus 19 columns. The modern value is 1.602. He was low by roughly 0.6%, and the reason is that he used a value for the viscosity of air that was slightly wrong, and the error propagated straight through. Two things about that experiment that are not in the schoolbook version. The first is a man called Harvey Fletcher. He was Millikan's graduate student, and he did an enormous amount of the actual work, including much of the early development. According to Fletcher's own account, published in Physics Today in 1982 after his death, they came to an arrangement. Fletcher would be sole author on a related paper, which he could use as his doctoral thesis. Millikan would be sole author on the charge paper. Millikan got the 1923 Nobel Prize. The second is worse. In 1978, the historian of science Gerald Holton went through Millikan's laboratory notebooks, which are at Caltech, and found that Millikan had discarded a substantial fraction of his droplets, while stating in the published paper that this was not a selected group of drops, but represented all of the drops experimented upon. Alan Franklin later did a careful reconstruction. Of 175 drops recorded over about 6 months, 58 were published. The notebooks contain comments in Millikan's hand next to individual measurements, remarks about which ones are beautiful and which should be thrown out. Franklin's defense, which I think is largely correct, is that the exclusions did not shift the value of the charge. They made the error bars look smaller than they should have. Millikan was not manufacturing a result, he was tidying one, because he was in a public fight with a Viennese physicist named Felix Ehrenhaft, who was getting droplets with fractional charges and claiming there was no fundamental unit at all, and Millikan believed, correctly, that Ehrenhaft was wrong, and he selected his data to make the case he already knew was right look cleaner than his apparatus could actually make it. And then, something happened that Feynman described in a commencement address at Caltech in 1974, and it is the most damning part of the story. Later experimenters measuring the electron charge did not jump to the correct value. They crept. The published values from the 1920s through the 1940s climbed steadily upward towards the truth, a little at a time. What was happening, Feynman said, is that when someone got a number much higher than Millikan's, they assumed they had made a mistake and went looking for the error until they found something to blame. And when they got a number close to Millikan's, they published it. Nobody was cheating. Everybody was being careful in one direction and not the other. It took the profession about 30 years to admit, by increments, that the founding measurement was off by 0.6%. I want to come back to the two men from 1897 now. because I left them in a lecture hall and a laboratory and I owe you the rest of it, and because what happened to both of them is about exactly this. About the gap between having the measurement and being willing to say what it means. Emil Wieschert, who told a room in Nigsburg in January of 1897 that there was something thousands of times lighter than a hydrogen atom coming off a cathode, went to Göttingen the following year and became the first person in the world to hold a professorship in geophysics. He did not stay with the electron, he built seismographs. The Wieschert seismograph, an instrument weighing over a ton with an inverted pendulum and a mechanical amplifying linkage, became the world standard for decades, and there are examples still in working order in observatories today. He founded the Göttingen earthquake station in 1901. He worked out how to infer the internal structure of the Earth from the timing of seismic arrivals, and the boundary between the mantle and the core is understood the way it is largely because of methods he developed. He died in 1928. He is in every seismology textbook. He is in almost no physics textbooks. The man who beat Thomson to the electron by nearly 4 months spent his career listening to the ground shake, and the reason he is not remembered for the first thing is that he described what he had measured and declined to announce what it was. Walter Kaufmann is the harder story. After 1897, having produced better numbers than Thomson, and refused to interpret them, Kaufmann went on to do something genuinely important. Between 1901 and 1906, he measured how the mass of an electron changes with its velocity using fast electrons emitted by radium, and this was the most sensitive test available anywhere of the competing theories of the electron. There were 3 candidates: Max Abraham's rigid sphere electron, which kept its shape as it moved; Alfred Butterer's model, which contracted in one direction and expanded in the others to keep its volume; and the Lorentz model, which contracted along the direction of motion, and which gave the same predictions as the new theory published in 1905 by a patent clerk in Bern. Kaufmann published his results in 1906 and stated that they were incompatible with the Lorentz-Einstein assumption. He had measured against Einstein and found Einstein wanting. In 1906, that was not a fringe position, that was the best experimental data in existence on the question, and it pointed the wrong way. Max Planck went through the analysis carefully and concluded the situation was unresolved. Lorentz wrote to a colleague that he was at the end of his Latin. Einstein's response, in a review the following year, was that Kaufmann's calculations appeared free of error, but that the theories his data supported had rather small probability because their assumptions about the mass of the moving electron were not suggested by any system of ideas of broader scope. Einstein was, essentially, refusing to be moved by an experiment. Not by dismissing it, but by saying that a theory answering to a wider set of concerns should not be abandoned on the strength of one measurement whose systematics nobody could yet see into. 2 years later, Bakura's experiments came out the other way. Then more. Kaufmann's apparatus had systematic errors in the field geometry that nobody at the time could have identified. And his data, painstaking and honest and better than anyone else's, was simply wrong. Walter Kaufmann held a professorship at Nigsburg from 1908 until 1935. He published less and less. He died in 1947 at the age of 76. Consider the shape of that life. In 1897 he had the best measurement of the electron in the world, and a philosophy that forbade him from saying it was a particle, so the credit went to a man in Cambridge with worse numbers. Then he built the best measurement of relativistic mass in the world, and this time he did say what it meant, and what he said was that Einstein was wrong. The one time he committed against the theory that turned out to be right. He got the caution wrong in 1897, and the confidence wrong in 1906, and he was one of the finest experimentalists of his generation, and there is no version of this where he wins. I am not telling you about Millikan in order to knock him down. I am telling you because we are now going to look at what the charge of the electron actually is, and you need to understand that the fixed number everybody believes in was never quite as fixed as the story goes, even at the level of the sociology. At the level of the physics, it is not fixed at all. Here is what happens around an electron in quantum field theory. The vacuum is not empty. Virtual electron-positron pairs are continuously appearing and disappearing throughout it. When there is a real electron sitting there, those pairs feel its field, and they orient themselves. The virtual positrons are attracted, the virtual electrons are repelled, and the result is a cloud of polarized vacuum surrounding the electron with a slight excess of positive charge close in. That cloud screens the electron. From far away, you do not see the electron's full charge. You see the charge minus the screening. And if you get closer, you penetrate deeper into the cloud, and you see more, which means the charge you measure depends on how close you get. This is no subtlety and no small correction. The fine structure constant, which is the number that encodes the strength of the electron's electromagnetic interaction, is famously about 1/137.036. That value is measured at low energy, which is to say at large distances, which is to say through the full thickness of the screening cloud. At the Large Electron-Positron Collider at CERN, physicists collided electrons and positrons at an energy of 91.19 gigaelectron-volts, the mass of the Z boson. That energy corresponds to a distance scale far inside the cloud. The Opal and L3 collaborations measured the effective coupling there directly, from the way the particles scattered. At that energy, the fine structure constant is about 1/128.9. The electron's charge, measured at short range, is about 6% larger than the electron's charge measured at long range. This is a measured experimental result from the 1990s, not a theoretical extrapolation. The number that every physics student is taught as a fundamental constant of nature is the value you get when you look at an electron from far away through a fog that the electron itself creates. Think about what that does to the idea of a property. Charge was supposed to be the thing the electron has. Mass got complicated by relativity and by the renormalization business. Size turned out not to exist. Spin turned out not to be spinning. Charge was the last simple one, the little minus sign in the corner of the diagram, and it turns out that the number depends on how hard you look, and there is no value of it that is the real one. There is only a function. A curve running with energy with no privilege point on it. The vacuum does not passively contain the electron. It responds to it. It arranges itself around it, and it decides, based on how closely you interrogate it, how much charge to let you see. And the electron cannot be separated from that response, because there is no bare electron underneath. The bare electron is the one with the infinite charge. It is not a physical object, and it never appears anywhere. What you call an electron is a disturbance, plus the vacuum's reaction to the disturbance. Those are not separable. You cannot peel the cloud away and find the particle inside, because if you could, the thing you found would have infinite charge and infinite negative mass. And the running does not stop. Pushed to higher and higher energies and the coupling keeps growing, and if you extrapolate the formula, it becomes infinite at a finite energy. That point is called the Landau pole, after Lev Landau, who found it in the 1950s. For quantum electrodynamics, it sits at something like 10 to the 286th electron volts, which is a number so far beyond any physically meaningful energy that it will never be reached by anything. But its existence says something, and Landau understood exactly what it said, which is why he spent the rest of the 50s arguing that quantum field theory was fundamentally sick and would have to be abandoned. Quantum electrodynamics is not a complete description of anything. It is an effective theory, valid over a range, which knows it breaks down and tells you so. It has a built-in expiry notice. I said earlier that each attempt to define the electron takes something away. That is the fifth. The charge does not belong to the electron. The vacuum reports it, and the report depends on the question. At this point, you might reasonably ask what is left. No size, no interior, no shape, no rotation, no fixed charge. What we still have is a countable, indivisible unit. Whatever the electron is, there is a definite number of them. They are all identical, and you cannot cut one in half. That is the last structural fact standing. In 2009, in a laboratory in Cambridge, a team took that apart too. The paper is in Science, volume 325, published in July of 2009. The lead author is Yodche Jompol, working with Christopher Ford's group at the Cavendish Laboratory in Cambridge, which is the same laboratory where Thomson worked 112 years later. The title is Probing Spin Charge Separation in a Tominaga-Luttinger liquid. Here is what they built. In a wafer of gallium arsenide, using electrostatic gates, they defined a set of extremely narrow channels, wires so thin that the electrons inside them cannot get past each other. In one dimension, if you want to move, everyone in front of you has to move. There is no going around. That constraint changes everything about how electrons behave, and it had been predicted to do so since the 1960s, in work by Shinichiro Tominaga and Joachim Luttinger. In one dimension, the ordinary description of electrons as independent particles bumping into each other stops working entirely, and what you get instead is a system whose excitations are not electrons at all. They are two different things. One carries the spin and no charge. It is called a spinon. The other carries the charge and no spin. It is called a holon. And they travel at different speeds. That is what Jompol and the Cambridge group measured. By tunneling electrons from the one-dimensional wire into an adjacent two-dimensional sheet and mapping how the tunneling depended on energy and momentum, they resolved two separate dispersion branches, one for the spin excitation and one for the charge excitation, with different velocities. The energy scales came out around 0.43 electron volts for one and 1.3 electron volts for the other. You put an electron into one end of the wire, its spin arrives at the far end at a different time from its charge. I want to be extremely careful about what that does and does not mean, because this is the exact point where science reporting goes off a cliff and starts writing headlines about scientists splitting the unsplittable, and that is not what happened. The electron is not being torn into pieces. A spinon is not a fragment of an electron that you could put in a bottle. These are collective excitations of the whole system, of all the electrons in the wire together, in the same way that a sound wave is a collective excitation of air and not a piece of an air molecule. Take the electron out of the wire and put it in a vacuum, and it is a single indivisible object again, exactly as before. That is the honest framing, and I want it on the record. Now here is the part the honest framing does not remove, and I think it is a great deal stranger than the tabloid version. Spin and charge are supposed to be intrinsic properties of the electron. Intrinsic means they belong to it, they define it. They are not circumstances but constitution. An electron with a different charge is not an electron. And what these experiments demonstrate is that in the right environment, those two supposedly inseparable defining properties become independent degrees of freedom that propagate through space separately, at their own speeds, obeying their own dispersion relations. If spin and charge were welded to a single object, that could not happen under any circumstances. No matter what environment you put the object in, you cannot separate the mass of a brick from the colour of a brick by putting the brick in a narrow corridor. The fact that this is possible at all tells you that spin and charge were never welded to anything. They are properties of the field configuration, and under the right conditions the field configuration can carry them apart. And then it got worse, in April of 2012, in Nature, volume 485. A team led by Justine Schlapper, working at the Swiss Light Source with collaborators from Dresden and elsewhere, used a technique called resonant inelastic X-ray scattering on a copper oxide compound, strontium-2 copper oxide 3, which is another quasi-one-dimensional material. They fired X-rays in, kicked an electron into a different orbital, and watched what came back out. What came back out was two things: a spinon, carrying the spin, and a second excitation carrying the orbital degree of freedom, which is to say the shape of the electron's distribution around the atom. That second one is called an orbiton, and its dispersion came out at around 0.2 electron volts, and this was the first time anyone had seen it. Spin, charge, and orbital. All three of the electron's degrees of freedom, all three of the things that in the textbook description are what an electron is, observed coming apart from each other and moving independently. That was published in Nature. It got a paragraph in the science pages. If you polled 100 educated people who follow science, I would be surprised if one of them had heard of it. There is no conspiracy in that. There is something I find harder to stomach than a conspiracy, which is that a result overturning the intuitive picture of the most familiar particle in existence is simply not the kind of thing that gets picked up, because it happened in condensed matter physics rather than in a collider, and condensed matter physics does not get the press office treatment. It goes further back than that too, and further out. In 1982, Daniel Suey and Horst Stramer, working with material grown by Arthur Gossard at Bell Labs, put a two-dimensional sheet of electrons in a very strong magnetic field at very low temperature and found plateaus in the resistance at fractional values. Robert Laughlin explained it in 1983 with a wave function that implied something specific and outrageous. The excitations of that system carry exactly 1/3 of an electron charge, not an average of 1/3, not an effective 1/3. Quasiparticles carrying a charge of E/3. Everybody assumed that was a mathematical convenience until 1997, when two groups measured it directly and independently within months of each other. One at the Weizmann Institute in Israel, led by Mordechai Heiblum, published in Nature. One at Saclay in France, led by Christian Glattli, published in Physical Review Letters. Both used shot noise, which is the statistical crackle in a current caused by the discreteness of the charge carriers. And the size of the crackle tells you the size of the lump. Both found 1/3. Later work found quasiparticles with 1/5 of an electron charge, and 1/4. And in 2020, two more groups, one at the École Normale Supérieure in Paris and one at Purdue, showed that these fractional objects are not fermions and not bosons. They are a third thing, called ennions, predicted decades earlier. When you swap two identical fermions, the wave function picks up a minus sign. When you swap two bosons, it picks up nothing. And when you swap two of these, it picks up a phase of 1/3 of pi. The Paris group measured the exchange phase directly with a collider built for ennions. The Purdue group measured the braiding phase, which is two exchanges, and got 2/3 of pi, which is exactly twice the Paris number, and therefore the same results seen from a different angle. The universe contains excitations that are neither of the two categories that every physics course teaches as exhaustive. I said the fractional charge results got a paragraph. That is not quite right. Suey, Stramer and Laughlin got the Nobel Prize in 1998, so it got more than a paragraph. But the framing was about a new state of matter, which is true and which is also the least alarming way to describe what had been found, and the sentence that would have made people sit up was not the one that got used. The sentence is this: the elementary charge is not elementary. In a two-dimensional electron gas at low temperature in a strong field, charge comes in thirds. Nobody hid that. It is in the citation if you read it properly. It is just that the version which reaches the public is always the version that leaves your model of reality intact, and this one does not. The most recent installment came in May of 2024 in Nature Physics. A group using neutron scattering on roughly 5,000 Co aligned single crystals of a Kagome lattice antiferromagnet found spectral evidence for spin-ons behaving as Dirac particles. Charge neutral, spin 1/2 excitations, obeying the same relativistic equation Dirac wrote down in 1928 for the electron, in a material made out of electrons carrying no charge. Which brings the count to 6. No size, no interior, no shape, no rotation, no fixed charge. And now, in the right circumstances, not even indivisibility, because the properties come apart. Therefore, we should stop asking what the electron is made of, because that question has now failed in 6 distinct ways, and ask instead the question that quantum field theory has been quietly answering since the 1930s. Not what is the electron made of, what is the electron a feature of? In 1927, 30 years after his father stood up at the Royal Institution and announced that cathode rays were made of particles, George Paget Thomson fired a beam of electrons through a thin metal film in Aberdeen and photographed the pattern they made on the far side. It was a set of concentric rings. Diffraction rings. The kind of pattern you get from a wave. At almost the same moment, Clinton Davison and Lester Germer at Bell Labs in New York were getting the same answer from a different direction, by accident. They had been scattering electrons off nickel, a vacuum flask cracked, the nickel oxidized, and in the process of baking it clean they accidentally turned their polycrystalline sample into a small number of large crystals. When they resumed, the scattering pattern had completely changed. They were now diffracting electrons off a crystal lattice, exactly as you would diffract X-rays, which are light. Davison and George Thomson shared the Nobel Prize in 1937. Joseph John Thomson won the Nobel Prize for proving the electron is a particle. His son won the Nobel Prize for proving the electron is a wave. Both awards were correct. Neither has ever been retracted. The father was still alive when the son received his, and died 3 years later, and as far as I can find, neither of them ever wrote anything suggesting they found this awkward. I find that restraint almost unbelievable. A family produced, across 2 generations, the 2 mutually exclusive answers to the question of what the electron is, and physics accepted both, and the standard resolution offered to the public is the phrase wave-particle duality, which resolves nothing. It is a label for the fact that neither answer works, and we have decided to use whichever one the experiment demands. Quantum field theory does have an answer, and it is neither of them. It is stranger than both, and it has been the working consensus among professionals since roughly the 1930s, and it has almost never been communicated to anyone outside the field. The answer is that there is one electron field, not one for each electron. One field, a single mathematical object defined at every point in space and time throughout the entire universe, extending through the room you are in and through your body and out to the edge of the observable universe and beyond it. That field is always there. It is there in what you would call empty space. It has a lowest energy configuration, which we call the vacuum, and it is not doing nothing in that configuration. It is sitting at its minimum, which is a state, not an absence. An electron is what you get when that field is excited by one quantum in a particular region, not a thing in the field, not a lump travelling through the field, an excitation of the field, in the same sense that a note is an excitation of a string. When a guitar string sounds an A, There is no object called an A that moves along the string. There is a string vibrating in a particular mode. If you ask what the A is made of, the question has no answer, because the A has no ingredients. There is a string behaving in a particular way and nothing else. You are made of these. Every atom in your body is a nucleus surrounded by these excitations. Every chemical bond holding your proteins in shape is a shared configuration of them. Every nerve impulse that has ever carried a thought across your brain is a movement of them across a membrane. Every colour you have ever seen was a photon absorbed by one of them, and every photon you have ever emitted, and you emit them constantly, came off one relaxing back down. And the field they are excitations of has no known composition either. Not a field in a medium, because the medium was the ether and the ether is gone. Not a field in space, in the sense of being carried by space, because in general relativity space itself is dynamical, it is the bottom. When you ask a physicist what the electron field is a field in, the good ones will tell you honestly that the question does not currently have an answer, and the less good ones will change the subject. There is a paper I keep coming back to, published in the American Journal of Physics in 2013 by Art Hobson at the University of Arkansas. Its title is a flat declarative sentence. There are no particles, there are only fields. Hobson's argument is that the experimental and theoretical evidence points to unbounded fields being fundamental and to bounded particles being an epiphenomenon, an artifact of how detectors respond, and that continuing to teach quantum mechanics in the language of particles is the source of most of the confusion in the subject. It is a good paper, and it made people angry. The journal published at least 3 separate published replies, one of which is titled, and this is the part that gets me, "There are no particles and there are no fields." Its argument, roughly, is that quantum fields are not fields in any ordinary sense either, that calling them fields imports just as much false intuition as calling them particles did, and that the honest position is that we have a mathematical formalism which predicts measurement outcomes and no agreed account of what it is describing. Read that exchange, and then consider that this is a debate in a teaching journal in the second decade of the 21st century about what the most common particle in the visible universe actually is, not about an exotic new discovery, about the electron. There is one thing about the field picture that is not disputed, and that I think is the single most underrated fact in physics. Every electron is identical, not similar, not identical within measurement error, identical in a way that has no analogue in the world of objects, because they are all excitations of the same underlying thing. And there is no more difference between two of them than there is between the note A played twice. There is no serial number. There is no where. An electron produced in the first minute after the Big Bang and an electron produced by a beta decay in your bones this afternoon are not similar particles. They are the same excitation of the same field, occurring twice. That identity has a consequence you can measure. Because the electrons are strictly indistinguishable, the mathematics requires their combined description to flip sign when you swap any two of them, and that requirement forbids two of them from occupying the same state. That is the Pauli exclusion principle, and it is not a rule about electrons being antisocial. It is a direct consequence of their being literally the same thing as each other. It is also the reason you have volume, your body's resistance to being compressed. The fact that your hand does not pass through the table is not electrostatic repulsion, whatever you were told at school. It is exclusion. The electrons in your hand cannot occupy the states already occupied by the electrons in the table, and forcing them closer costs energy, and that cost is what you feel as solidity. You experience the indistinguishability of the electron every time you sit in a chair. And while we are dismantling the classroom picture, there is one more piece of it that is worth taking apart. because it is the piece almost everybody gets wrong, and it goes directly to what we are talking about. Picture the wiring in the wall behind you. When you flick a switch, the light comes on immediately, and the mental image nearly everyone has is of electrons racing along the copper at close to the speed of light and slamming into the filament. They are not racing, they are crawling. Take an ordinary copper wire, about 1 millimeter across, carrying about 1 ampere, which is a modest household current. Copper has roughly 8.5 times 10 to the 28th free electrons in every cubic meter, which is an enormous number, and because there are so many of them, each one only has to move very slowly to deliver that current. Run the arithmetic, and the average drift speed comes out at around 0.07 of a millimeter per second. That is about 1/4 of a meter per hour. If your light switch is 1 meter from the bulb, an individual electron leaving the switch when you flick it will arrive at the bulb roughly 4 hours later. The light obviously comes on instantly, because what travels down the wire at close to the speed of light is not the electrons at all. The electromagnetic field configuration does the travelling, the change in the state of the field, propagating along the outside of the conductor and reorganizing the drift of every electron in the circuit almost simultaneously. The electrons are not the message. They are the medium, and they are barely moving, and on top of that slow drift they are jittering around at speeds over 1 million meters per second in random directions, so the drift is a tiny statistical bias imposed on a violent thermal chaos. Every electrical device you have ever used works by the field, not by the delivery of particles. The particles crawl. I bring that up because it is the same lesson in a different costume. What we call the behavior of the electron keeps turning out, on inspection, to be the behavior of the field. The particle language survives because it is convenient for bookkeeping, and because detectors go click, and every time you look at a case closely enough to see the mechanism is field. And people have tested it, because if the argument is that good, someone should check. There is an experiment called VIP for violation of the Pauli exclusion principle running deep underground at the Gran Sasso National Laboratory in Italy under a mountain of rock to shield out cosmic rays. It passes a current through a strip of copper and looks for X-rays of an energy that could only be produced if a new electron entered an already full shell. The second-generation experiment set an upper limit on the probability of such a violation at 3.4 times 10 to the minus 29. Nothing has ever been seen. To the best of anyone's ability to check, the identity is exact, which raises a question that John Wheeler asked out loud in 1940 on the telephone to his graduate student Richard Feynman. Feynman recounted it in his Nobel lecture. Wheeler rang him up and said he knew why all electrons have the same charge and the same mass. It is because they are all the same electron. The idea is that a single electron weaves back and forth through time, forward as an electron, backward as a positron, threading through the entire history of the universe, billions upon billions of times, and every point where the world line crosses any given moment is what we call an electron in that moment. Feynman asked the obvious objection, which is that there would then have to be as many positrons as electrons. And there are not. The idea is wrong. It also survives in the physics, because Wheeler's reasoning about a positron being an electron moving backwards in time became the standard way of handling antiparticles in Feynman diagrams, which is Feynman's Nobel Prize. And I bring it up because of what has to be true for the question to even be askable. Wheeler could seriously propose that every electron in the universe is the same electron, because there is nothing about any individual electron that could distinguish it. No mark, no history, no interior state, no identity of its own. He was not being fanciful. He was following the indistinguishability to its most extreme reading. And the only thing that killed it was a counting argument about positrons. counting, again, that is the thread I keep pulling and it keeps coming back. We have lost the size, the interior, the shape, the rotation, the fixed charge, and the indivisibility. What remains, and it is the only thing remaining, is the number. There are however many electrons there are. You can count them. Detectors click, and each click is 1, and the clicks are integers, and integers are the last solid ground in this entire subject. In 1976, a Canadian physicist working on black holes published a paper that removed it. To see why that paper does what it does, you need one more piece, and it is the most famous experiment in physics, done properly, with the right names attached. In 1974, 3 physicists in Bologna, Pier Giorgio Merli, Gianfranco Misiroli, and Giulio Pozzi, took an electron microscope and modified it. They inserted a device called an electron biprism, which is a fine-charged wire that splits an electron beam into 2 paths, and they turned the source down so low that at any given moment there was at most 1 electron inside the entire apparatus. Then they filmed the detector. What appears on the screen at first is a single dot, then another dot, somewhere else, apparently at random, then another. For a long time it looks like nothing, like static, like noise. And then, as the dots accumulate into the thousands, an interference pattern assembles itself out of them. Bands, the signature of a wave passing through 2 openings and interfering with itself. Each electron arrived as a single localized dot. The distribution of the dots is a wave. Akira Tonomura and colleagues at Hitachi in Japan repeated it with better technology and published in 1989, and their film is the one everybody has seen. In 2002, readers of Physics World voted the double-slit experiment with single electrons the most beautiful experiment in physics. The award was widely reported as being for the Tonomura work. It took a letter to the editor from a Bristol professor in 2003 to get the Bologna group properly credited for having done it 15 years earlier. Every account you have ever heard of this experiment asks the wrong question. The question everyone asks is which slit did it go through, and the answer tediously is that the question does not have an answer. And there are a dozen interpretations arguing about why. The question that matters for us is different. Where was the electron between the source and the screen? The honest answer from quantum field theory is that there was no electron between the source and the screen. There was a field, evolving deterministically, spread across both paths, doing exactly what a wave does. What made a dot was the detector. The dot does not show you the electron arriving. It shows you what a detector does when a field carrying that much energy interacts with a screen made of atoms. The particle is not what travels. The particle is what the detector reports. And that is the setup for what Bill Unruh published in 1976, building on work by Stephen Fulling in 1973 and Paul Davies in 1975. The question they were asking came out of black hole physics, where Hawking had just shown that black holes radiate. Unruh asked a stripped-down version of it. Take a quantum field, put it in its vacuum state, the lowest energy configuration. The state an inertial observer would call completely empty. No particles, nothing there at all. Now take a detector and accelerate it through that vacuum at a constant rate. It clicks, not from a malfunction, not from noise. The accelerating detector registers a thermal bath of particles with a genuine temperature proportional to the acceleration. The faster you accelerate, the hotter the vacuum gets. An observer floating alongside sees absolutely nothing and correctly describes the region as empty. The accelerating observer sees a warm gas of particles and correctly describes the region as full. Both are right. There is no experiment either of them can do to prove the other wrong, because the disagreement has nothing to do with measurement error. What they disagree about is what counts as a particle, and the answer depends on how you are moving. The temperature is tiny for anything you could build. To get 1 Kelvin, you need an acceleration of around 10 to the 20th meters per second squared, which is about 10 to the 19th times Earth's gravity. Nobody has directly observed the Unruh effect, but it is not a fringe proposal or a contested speculation. It is a straightforward consequence of quantum field theory in curved and accelerated frames. It has been in the textbooks for 4 decades, and it is intimately connected to Hawking radiation, which essentially nobody in physics doubts. What it establishes is this: the number of particles present in a region of space-time is not a property of that region. It describes a relationship between that region and an observer. The field is real. The field is there for everybody, and everybody agrees about it. The particle count is not, and it never was. That is the last thing gone. We started with an object, a little ball, in a diagram, on a wall. We took away the surface, because nothing has ever bounced off it. We took away the interior, because its own lightness will not permit one to exist without a fine-tuning of 1 part in 400,000 repeated separately for every particle in the standard model. We took away the shape, because when you ask general relativity to describe it, you get a singularity with no horizon over it. We took away the rotation, because the surface would have to move faster than light, and what is left is angular momentum with nothing turning, and if you rotate it once it comes back inverted, and that has been measured. We took away the fixed charge, because the vacuum screens it, and the value you get depends on how hard you look, and there is no true value underneath. We took away the indivisibility, because in a wire narrow enough its spin and its charge and its orbital shape come apart and travel at different speeds, and that is in science and in nature, and nobody told you. And now we have taken away the count. There is no answer to the question of how many electrons are in the room with you. There is an answer relative to you. Sitting still. There is a different answer relative to something accelerating past you. Neither of you is making a mistake. I said at the beginning that Hans Dehmelt named a particle Priscilla, and that a particle isolated for that long deserves a name the way a pet does. I have thought about that sentence more than anything else I read for this. Because what was in the trap was not a small object being kept in a box. There was a region of space in which a field was in a particular excited configuration, held there by the shape of some other fields, for 3 months, and every time Dehmelt interrogated it, it answered consistently, and the consistency of the answers is the only thing that made it an it. It had no inside for him to look into. It had no surface for him to see. It had no size, no substance, no fixed charge, and no meaningful position. What it had was a persistent pattern of responses. He gave it a name because it kept answering. That is the entire content of thingness here. Something that keeps answering the same way. And you are made of these. Not out of them, the way a wall is made out of bricks. There are no bricks. Every atom in your body, every bond in every protein, the exact shape of your face, the reason you do not fall through the floor, the entire electrochemical cascade that is producing the thought you are having about this sentence right now, all of it is the behavior of excitations in a field that has no known composition, in a state that no observer can absolutely count, described by a theory whose central calculation its own authors called hocus pocus and not sensible mathematics, and which works to 13 parts in 100 trillion. The physics is not incomplete in the way a jigsaw is incomplete, with a hole in it the right shape for a missing piece. The physics is complete and predictive and the most accurate description of anything human beings have ever produced, and it does not contain an answer to the question, and there is no evidence that it is supposed to. Thomson called them corpuscles. little bodies. He was hedging in a way, because he knew he could not see them and he wanted a modest word. It is the most inaccurate word in the history of physics, and it is still the picture almost everyone carries. Because 129 years later, nobody has produced anything better to put in its place. And the thing standing where the picture should be does not have edges you could draw. You will not notice any of this tomorrow. The floor will hold. The light will come on. The chemistry will proceed. Nothing about the world changes when you find out that the substance underneath it is not a substance. But there is nothing down there. Not a smaller thing we have not found yet. Not a deeper layer waiting for a bigger machine. The bottom of the stack, the thing that everything else is made out of, is a pattern that answers questions when asked and has no properties in between the asking, in a number that depends on who is counting. It has been like that since 1897. Nobody mentioned it,